Alright, welcome back to Meteorology 101. In this video, I'm going to talk about weather observations. So, pretty much what they are, when they're reported, and what we can use them for as forecasters. So, a weather observation is a METAR that is sent out from pretty much every weather station throughout the United States or any airfield that once an hour that gives you winds, temperatures, dew points, sky conditions. Some are automated, some have weather observers involved. So let's get into the video. A METAR observation, here's an example. KILN, station identifier, everything. This isn't everything that's in a METAR, but it is the necessary reports, all the data that's reported. In remarks, you can have numerous things throughout remarks. That's up to the observer, kind of what they want to put in there, anything they feel is significant to that weather station. So, station identifier, KILN, that's Wilmington, Ohio. Date and time, the date is the 31st, it says August 31st, and the time is 22:54Z. So, these are sent out every hour. You'll see that time to be pretty close to the top of the hour, or typically not right on the hour. You'll see it about 5 minutes or less before the top of the hour. The auto means this is automated. There is an ASOS, an automated surface observation system at this location, so there is no human interaction involved in this observation at all. Winds were reported at 280 at 8 knots. From 280, winds are always from the first 3 digits of your direction. The winds are always from that direction. And the last 2 digits are your speed. Now, if there's a gust, then you'll see a G, and then you'll see 2 more digits, another speed. 10 SM is the visibility. Anything above 7 miles is considered unrestricted. For aviation, you'll typically see 10 miles visibility in anything that's unrestricted. If it's unrestricted, they'll put 10. Anything below 7, they have to have an identifier, a weather identifier reported after that to indicate what's restricting that visibility. At the minimum, it has to be mist. It can be mist or haze, rain. But if it's below 7 miles, there has to be weather reported. Few at 6,000 feet. 060 is 6,000 feet. If it was 006, that would be 600 feet. And if it was, say, 200, that would be 20,000 feet. Typically, what you see is a 200 or 250, maybe sometimes a 300 on some serious clouds at 30,000 feet. Pretty much the highest you're going to see a cloud layer. Typically 20 to 25,000. Temperature 26 degrees Celsius. Dew point's 13 degrees Celsius. Altimeter's 3002. And then in your remarks, AO2 is the automated system, and SLP is your sea level pressure, and that is in millibars. So it's 1,016.1 millibars. And then temperature for this time, the zero, the T, you have the T for temperature. 0 means positive. It's a positive temperature. If that was a 1, it would be a negative. But it's a positive temperature of 25.6 degrees. And then another 0 that indicates a positive dew point, and that is 13.3 degrees Celsius. All temperatures are always reported in Celsius, unless you're looking at a surface map, then you'll see them in Fahrenheit. Which we'll pull up a surface map and we'll show how these METARs are plotted on a surface map for each station. So you have the station identifier, date and time, wind direction and speed, visibility, sky condition, temperature, dew point, station pressure, and your remarks. This is the code for a METAR. So you can run a METAR. It's a meteorological airdrome report, or you can run a special. A speci is anytime significant weather starts or stops. So rain starts or stops, snow starts or stops, visibility drops below 3 miles, ceiling drops below 3,000 feet. There's a lot of criteria to run a special. The thunderstorm begins, thunderstorm ends. And then this is pretty much everything we just covered, but it's in code to show you, just for learning purposes, for weather observers. When they go to school, they got to learn this code, and then how to identify what parameters what and where to put it. So, like if you look at the winds, direction, speed, gusting, to what speed. So, and it's always in knots. Now you can have variable winds, your minimum direction, say 010, V is for varying, say 190. So you could have winds varying from the northeast varying to the southeast. Typically you'll have anything less than 6 knots can be a variable wind. Visibility, runway visibility, that's measured in feet. Present weather, and sky condition. We'll go through each one of these so you don't have to learn the code. This is just a touch base and look at what a weather METAR is, and then we'll break it down onto the weather charts to show you how you can use it and how it's used in weather to get those charts. It's a weather observation sheet, and it's hard to read, but every hour each one of those lines are filled out unless a special METAR is required, which is weather starting or stopping or any significant weather that has to affects aviation. All right, so wind direction and speed is measured about 30 feet above the ground and is a 2-minute average. Direction is measured in degrees in which the wind is from. Remember, winds are always in a from direction and reported to the nearest 10 degrees. May be reported variable when the speed is less than 6 knots, and gusts are only reported if winds exceed the average wind speed by 10 knots or greater. So if the average wind speed is 10, then you're going to be gusting to 20. So if you have, because pretty much your winds are going to be, the speeds are going to be variable anyway, but the ASOS takes an average, a 2-minute average, and then if your wind gusts, or I mean, you can have gusting to 15, but you pretty much it says you have to exceed the wind speed of 10 knots or greater. I've seen gusts to 15, but typically if you look at the station plots, you'll see a 10-knot wind on a 10-knot flag, and then a red half of notch, which is 5, so it's like 10 gusting to 15, but it could really be, say, 7 or 8 knots gusting to 18 knots. So you got your 10 difference there. That's where I could say 10 gusting to 15 by looking at a station plot. We'll see if we can find one of those on the surface chart and show you what I mean by that. Gusts are reported. Okay, we just covered that. All right, variable wind direction only reported if the winds are varied 60 degrees or more. So if you got 010, you got to be at least 070 to be variable. Pretty much, weather observers don't typically go out there with an anemometer and try to measure the wind. That's all done by the ASOS. There's still an ASOS on every station, and then the weather observer uses most of that data off the ASOS. The only thing they're really there to report is they'll verify the temperatures with a dry bulb, wet bulb, and on a sling psychrometer they can verify the temperatures, and then they're looking mainly for the cloud conditions, the sky condition for cloud coverage. And then the ASOS will shoot one beam up, straight up, and give you pretty much a cloud layer, unless it goes through that cloud, hits another one. But if the clouds are too thick, it's only going to show you one layer. So that's why it's important sometimes, some airfields, a busy airfield, to have an observer go out and look at the different layers of the sky. Visibility is a horizontal surface visibility or the runway visual range, reported in statute miles. Prevailing visibility is reported. Values given in a specific direction is known as sector visibility. So you can have, unrestricted visibility throughout your station, but you have one area. If you have a little bit of swampland or something, you get fog in that area, then you can say sector visibility is southeast. That would be put in remarks, would be sector visibility southeast, like 3 miles or 2 miles, whatever that sector visibility may be. Runway visual range, we don't really have to worry about that. That's for aviation. If the runway has fog on the runway, then the active runway is 6,000 feet or less, where the visibility is less than 1 mile. Sky condition, the code for sky condition is the coverage and the height. You can go vertical visibility, if total overcast. If it's foggy out, you can't see the sky, you look up, you estimate how far you can look up in the vertical to report vertical visibility, or you go SKC. Sometimes you see that a CLR for clear skies. That means there is no clouds in the sky whatsoever. If there's one cloud in the sky, you have a few condition. So cloud amount measured in octaves, so you break the horizon up into 8 parts, and then that's how you determine your cloud amount or sky condition. Clear, CLR, SKC indicates no clouds at all. Few is 1 to 2/8 of the sky is covered, and that's all together. So you'll have clouds throughout the horizon, but you add up, if you take all those clouds and push them to one side, it means only 1 or 2/8 of the sky is covered. If you hit 3/8 of that sky covered, then you go scattered. 3 to 4, and then anything 5 to 7 is broken. That means you can see one little area of blue sky, or just 5/8 of the sky is covered. So you can still see some blue sky, but if you have 7/8 and you got one little hole, you look like you're overcast, but you see one little hole of blue sky, then you're still broken. It has to be completely covered to be overcast. That's 8/8 of the sky is covered. Cloud height, the base of the layer of the cloud above ground level. So like we said with the ASOS, that will shoot one beam straight up, hit the base of the cloud, and give that a reading of how high that cloud is. Now, for an observer, you got to go out, look at the sky, see if the different layers, and then report each layer, so you can have, few at 3,000 feet, scattered at 5,000 feet, broken at 10,000 feet. So you can have 3, you can have 4, you can go all the way until you hit broken or overcast, whatever that last layer of coverage is. And measure to the nearest 100 or 1,000 feet, depending on how high you go. So anything less than 50 feet is pretty much 0. 5,000 feet or less, you round to the nearest 100 feet. 5,001 to 10,000 feet, you measure to the nearest 500 feet, and above 10,000 feet, round to the nearest 1,000 feet. So cloud coverage you don't have to worry about. Now, if you're flying a drone, you do need to figure out how to estimate cloud heights, because you're only allowed to go up to 400 feet in a drone. So, but you got to stay 1,000 feet below the clouds. So, basically, if the clouds are 1,400 feet, you're allowed to fly your limit. But if the clouds are at 1,000 feet, you're really you're not allowed to fly. You'd have to be basically 1,100 feet. You can fly at 100 feet. So you got to know those cloud heights if you're going to fly a drone. Temperature is measured in a sheltered location over a grassy area with no unusual heating or cooling. So AC units, anything going to produce heat or have air blown across, they will not have the thermometers out there. The ASOS won't even be out there. It's usually out on the runway, next to the runway, to get those readings pretty much out in the open. Typically measures about 5 feet above the ground. Cold air accumulates closer to the ground, so temperatures can be reported above 0 and still have frost on the ground. So you can be at 0 on the surface, frost on the ground, but you're measuring 5 feet above the ground for the temperature, and you could be 33, 34 degrees Fahrenheit. Dewpoint indicates the amount of moisture in the air at the weather station, determined using the wet bulb thermometer. There's a calculation. We used to use a sling psychrometer, so we had a dry bulb, regular thermometer, and we had a wet bulb. We put a little sock over the second thermometer, and we would sling that for about 30 seconds in that shaded area above the grass, and then get our readings and do a calculation to verify that the ASOS was accurate. Latest determination tool is the ASOS. We talked about that, which uses controlled refrigeration of a small mirror to produce condensation detectable by an infrared beam. So these things been around for a long time. They do most of the work. Station pressure is sea level pressure. The station pressure reduced to sea level. The correction from a pre-computed R factor, which is based on the average between the current temperature and the temperature 12 hours ago. Helps remove temperature bias. Sea level pressure is used on surface maps. We'll see that here in a little bit. and standard sea level pressure is 1,013 millibars. Trying to think of that in HPA, hectopascal. Can't remember off the top of my head. So remarks, there are several available remarks that can be reported on either a METAR, a special, or both. So there are several remarks here. It's going to end that show, but for the special remarks, real quick, what you're going to like sector visibility is one. Virga, if it's raining but the rain is evaporated before it hits the ground. The hailstone size, if there's hail, you're in a thunderstorm. If you have distant lightning, what direction that lightning is in, if you have a distant thunderstorm. Frontal passage, if you had a wind shift due to frontal passage, you could put FROPA in your remarks. A peak wind, tornado activity. If you have a variable ceiling, obscurations, anything, stop smoke. If there was a local fire and the smoke was blowing through, reducing visibility in one sector, you go sector visibility, and then you can report that what that is in your remarks for sector visibility. Your sea level pressure is always in your remarks. If you have an aircraft mishap, if that's in there, you'll see that. Pretty much thunderstorm locations, talked about that. And then all like lightning types. You'll see like in cloud, cloud to ground, cloud to cloud. What type of lightning, that'll be in the remarks also. If the observer, feels that's necessary to put in that report. So we'll go look at some reports and see if we see any specials. I'll pull up like 48 hours at a station, and then we can see, get a good look at what we're looking at for the observations. Try to break this down a little bit more. Okay, here's a list for CVG. This is for Cincinnati. So we pulled the last 48 hours raw data at CVG. Okay, so if we go back through, we had a storm come through the other night. But you can look at the clouds. A lot of fog in the next morning as temperatures dropped. We had a frontal passage, so temperature dropped, but after all the moisture from the rain and then the cold air over that warm, moist surface pretty much caused evaporation and then reduced visibility significantly. So we'll go through some of these, take a look at the remarks, and then after this we'll pull up a surface chart, not of these observations. We'll pull up the latest surface chart and then download the latest data and see what's going on there. So we look at some of these, we see 2 miles visibility with mist. Like I said, if your visibility drops below 7 miles, you have to have an identifier, a weather type. What's happening? What's reducing that visibility? BR is mist. There's a whole page of code for this. Like HD is haze, RA is rain, and then you'll see like a identifier in front of that rain, like drizzle. Right here we have drizzle, DZ. We have a negative sign that says light drizzle. With no sign at all, that's moderate drizzle, and then a plus sign would be heavy drizzle. So typically you won't see heavy drizzle, it's just drizzle. The definition of drizzle is the droplet is less than 0.5 millimeters. So if it's greater than 0.5, then it's rain. It's a raindrop, so it's light rain. Now you're not getting out there and measuring those drops, but you can tell if a raindrop is just kind of floating around. They will fall, drizzle will fall, but it's kind of more or less staying afloat. It's real buoyant, and they will still fall, but you can tell when it's just drizzling out. You get that real light moisture. Your skin's still getting wet, versus a raindrop that's just strictly dropping to the ground. So overcast 300 feet. So this is done by an observer. There's no audio on this. The AO2 I know I said that was auto earlier, but that's not. There's something else there. It has an ASOS on at that station is what that means. There's an ASOS. I think second generation is what that means for. That's what the instrument that's being used to get most of this data. Now, like I said, with the ceilings, that ASOS will only shoot one beam up. So these ceilings are reported by that observer. Now, there's a lot of different ways to estimate your ceiling, SCU-T charts, moisture levels, upper air charts, stuff like that. So they got a lot of ways to be pretty accurate on what those cloud heights are. Even with the pilots, if they're on an air station, they can get a pilot report. Any pilot in the area, they can call out and get a pilot report and know what the winds are at their flight level, what these cloud layers are, and get a lot of data there. So now there are pilot reports that are put out too. As pilots report those, then the weather station types those up and reports them too. We're not going to cover that, but because we're just sticking with the observer data, the METARs. I mean, to sit here and go through this, you can pretty much tell what happened. You can base a forecast off of this to some point, but you need to understand what's happened to understand what's going to happen. So you look at this for the past to determine the future. So you can try to get a picture of the atmosphere. Then you go out and you look at the sky. You got to learn how to read the sky. So winds pretty much westerly at 10 knots coming from the west, 290, 10 knots, unrestricted visibility, scattered 1,200 feet, overcast 2,000 feet. So here's one with 3 layers. We got few 1,200 feet, scattered 2,200 feet, broken 3,400 feet. So anytime you see a 0, then you're only in the thousands. So you can go 10,000s. So you see 25,000 feet. Let's go back up here. We got a few of 5,500, clear. Sometimes you'll see some cirrus reports. Overcast. Let's see where to see it. 6,000 feet. 6,000, 6,000. So I'm looking, see if there's anything. There's a 12,000. Typically, like I said, you'll see a 25,000 feet if there is cirrus out there. So light rain, scattered 10,000, scattered 12,000. Dewpoint, temperature and dew point is 21 degrees, 100% humidity. Now we look at these other remarks. Once we get to the remarks, station pressure 2991, 2992. That was the altimeter. That was the other station pressure. Just at a standard atmospheric pressure. That's the 2991. 2992 is standard atmospheric pressure in the English measurement. AO2 is there's an ASOS on board. Lightning distant to east through south. So there's distant lightning that reported that this time. They only had light rain at the station. Thunderstorm began 07, so 7 minutes after. And then don't show when it ended, but there's another thunderstorm began at 14 after and then ended 43 minutes after the hour. Sea level pressure was 120. P0006 is how much precipitation there was. There was 6/10, 0.06 tenths in the last hour. 6.5 is there was 6.5 tenths in the last 6 hours. And then temperature, this breaks down the current hourly temperature, and that is that positive. 0 is positive, it's 20.1 degrees, so we're reporting rounding up to the nearest whole degree, 21 degrees. And then 20.6 on dew point also, we know that's positive because of the 0, and that is also 21 degrees rounded up. The 5 is station pressure. So this second digit means, it can mean of several things. So rising rapidly, station pressure rising rapidly, falling rapidly, but the station pressure changed by 0.12 in the last hour also. So that shows the pressure change. Now on a 6 hourly ob, you have 3 hourly obs, 6 hourly. These are reported every hour, but you still have 3 hour obs, 6 hour obs, 12 hour, 24 hour. You can get a little bit more data from those observations also. So if we looking for like an 18Z, 1752 would be the 18Z. So that's when you get that extra data. Now you have precipitation in the last hour. Uh, 5 is the pressure change. 2, let me look that one up real quick because I can't remember the 2 off the top of my head. Let's see if I got a 2 in here. No, I don't have that on my chart to have that readily handy, so I'd have to go through the code, find what 2 is. But you have several different remarks you can put in this. Alright, so you'll see what type of weather, what the ceilings are. Vicinity thunderstorms, light rain, scattered 900. Now typically on this also, if we have a thunderstorm, let's go find one, you'll see what layer the base of that thunderstorm, that cumulonimbus cloud is. Alright, thunderstorm and rain right here. So scattered 900 feet, so they're saying the bottom of that thunderstorm cloud, the CB, is 900 feet. So they put a CB at the end of that. Okay, we're going to go to pull up a surface chart and look at these plotted on a chart. Now, we only put up one station here, so you on the chart you only see one station at a time. What you'll see is that latest observation, and then that'll be plotted out into a station plot. Let's go down here and see if this shows us what we got. Now, let's go to METAR Home real quick and look at this. We should see, actually you can see all this data. As you scroll up and down, it zooms in and out, so you gotta be careful with that on this. Okay, so like CVG, there's your current observation. You just hold the mouse over, that tells you what, that just pretty much tells you what the observation was, and then you can see here is what it's plotted to. So your altimeter's in the top right, ceilings directly to the right, station identifier. Now the surface map that I show doesn't show all this because it will get way too cluttered. This one actually shows it pretty good, but as you zoom in, zoom out, these things can get really cluttered. But here's a 10 knot wind gust in the 15s. So there's a perfect example of, we said it's got to be a 10 knot difference, but so you got to count this 10 knot wind could be 7. It's most likely like a 7 knot wind, and then that 10 could go up to 12. So you got, or 15 17, that could go up to 17 knots. So gust in the 17. So there's probably 7 knots gust in the 17. Let's see what it is. 10 knots gust in the 17. So I don't know why it says you have to have a 10 knot increase on your winds for a gust. With the peak wind, they're showing that in the remarks. That was 230 at 20 at 2217 at the time it happened. Alright, so this is your station plot. These are all the plots here, which is pretty cool. You can go to this site, aviationweather.gov, pull up METAR. You can look at your current conditions. So like this one, temperatures on top left, dew points bottom left. So when you start looking at these dew points, there's a 66, 66. There's where you can have some significant weather if you got the right conditions for thunderstorms to come through. And you got dew points that high, then you're start looking in the severe area for weather also. Alright, about 60, 61 or above on the dew point is pretty much what you're looking for to determine if any of those thunderstorms could be severe. Alright, so let's go to pull a surface map. Okay, I got the radar overlaid on this map. This is my weather software, digital atmosphere. I can download the data, save it, and then, well, if I lose internet connection while I'm out on a storm chase or something, I don't have to worry about, okay, pulling a latest surface map to find out what's going on. I got at least one surface map I can work with and find out what the data is, and then determine what area I want to go to. So I can pull up each state individually if I want to, which most likely what you do on a chase, and then you pull that surface data, look at the overall synoptic situation, and then determine where you're going in from there. So if we pull up the station plots, I'm only going like 85% crowded on here. If I did 100%, you wouldn't be able to see the screen. So I could pull 85 to 87% to get a good idea what's going on with this surface chart. So we'll throw the surface plots on here first. Takes just a few seconds to process. Okay, so this isn't like the aviation weather site where you can put your mouse over and it tells you, it breaks down that data, which I'm not too concerned about that. I'm looking for wind directions, wind speeds. I got the radar overlay on this so I can see my significant weather. If we go down here in Texas, we can see some convection. Nebraska, see some convection. We'll pull up the radar. I got another radar program I use for the radar, so we'll pull up that radar and go into some of these radar shots and break it down even further. So when we get into a chase, we can actually do volume scans and cross sections and break them storms down and find out where the most severe part of those storms are. Tornadoes always occur in the southwest quadrant of a thunderstorm. But you can have multiple thunderstorm cells, so you need to kind of zoom in on those, break those down, and then go from there where you're going to go in for that chase. Now I can download these plots over that radar too on my radar program, and then they'll have a pop-up like the aviation weather, and then give me that data that I need, and actually a lot more than what just aviationweather.gov does. So if we look at this, we can see winds out of the southwest, kind of going southerly, southeasterly, and we got one out of the north right there. So we almost got a wind shift right there. So we may be looking at some rotation. Winds opposing each other right here, so you have low level divergence. Not really probably reaching that far out, but the winds, depending on how far these winds come out, not just from that station, but the winds are blowing in this area too. There's just not a station there to report it. So these two winds colliding right here or opposing each other, you could have a frontal boundary right there. So you have a warm front, maybe a low pressure system right here, a warm front, and then you look for maybe a cold front coming out here. But the winds, they're not really identifying that, because you would have usually a northwesterly and then shifting to a southwesterly to break that cold front. So 80 degrees, 75 degrees is only a 5-degree difference. There's 68, so there's a little bit of a colder center there. 84, so you could have a little bit of a cold front coming out here. 86, 68. You'd have to place your low probably a little bit further to the north and bring it back if you had a front associated with that. But I know there was there was a warm core low here, been sitting over Texas for pretty much weeks now. There's an 88, 86, 80, 92. So we got a pretty good warm area there. We'll put the lines of equal temperature on here. You typically won't find those on a surface chart. I always put them on my surface chart because I want to see where my thermal advection is, where my warm pockets, cold pockets are, and then it gives me an idea where my thermal advection is, and we can actually zoom in on those storms a little bit just based on that data. So I'm going to put sea level pressure on here. We'll analyze all these sea level pressures. 1014.9, 1015.3. Anything you see with a 1 in front of it, you'll put a 10. Anything that you see a 0 in front of it, you'll put a 9. So we will go sea level pressure. Alright, looks like low right there. I'll probably bring it a little bit to the north, but these are computer analyzed. I mean, that's not bad. The rotation, you can see it right there. High pressure. Do we have the high? We do have some ridging right there because of the anticyclonic flow. That wind is coming out of that high, which that's correct. Winds blow clockwise and out of a high pressure system. Calm winds in the middle. You'll have calm winds in the middle of the high. Calm winds in the middle of the low, but we don't have a station there to report that. So we have clockwise rotation, counterclockwise rotation. So there's got to be some sort of boundary here separating us. Maybe that front, that warm front right there. We'll put the fronts. They're computer-generated fronts. I take them with a grain of salt. You got to look at this data and verify those fronts. But we have that parent low up to the northeast. So here's a wind shift, pretty strong wind shift right there. So you put your frontal boundary right through that trough. Looking at temperatures, 58 and 68. So I would break those two in half with the front. 70, 62. So definitely a front right there. It looks like another prefrontal trough ahead of that. And then bring that back, and that would more or less go into a stationary front between maybe this high and that high, and then come back into that little bit, maybe a warm air advection, if any, right in that area coming into that low. All right, so let's put the thermal advection on there. Let's put the isotherms on there. All right, so this is a cold core system, 24 degrees Celsius. I always hit Celsius because Fahrenheit gets a little cluttered, but for this purpose, let's stick with Fahrenheit. I'm going to remove that. We'll go with the Fahrenheit isotherms. So there's our 88, 86. There's 78, 76, 74. So we're still pretty warm there, but it is a cold core system down here. Here's 82 and 80. That's a cold core high. And then trying to see what we got going on right here. So real tight thermal gradient. But Fahrenheit always does show up real tight thermal gradient. These are every 2 degrees. Even every 2 degrees on Celsius, it doesn't pack it that tight. But Fahrenheit it does. That's why I usually use Celsius, because I'm just looking for thermal advection anyway to verify where my cold front is. So if we had thermal advection, we would say it's all in this area. Let me get a draw tool up real quick. I can show you. All right, let's go back. Where my mouse is, I'm stuck. Okay, here we go. All right, there's the front. Thermal advection, pretty much where these isotherms cross. So that's all cold air advection right there. Isotherms are crossing here, cold air advection. Really not much going on right here. So we're nothing here. All of our cold air advections there, so we put our front and bring it back, maybe toward this way. It's going to stall out, but this high, you have to question now, is that high really there? Because typically that high will be behind the cold front. But you can't really bring this front down here because you just don't have the thermal advection to back that up. 84, 79, 86, 84. I mean, you're only 2 degrees there. 77. You're colder there than you are back here, so you can't verify that one either. 80, 77 is only a 3 degree difference, so like I said, you can't really bring that back. You'd have to bring that front back here. Let's throw the computer generated fronts on and then see where we are there. That's typically they're way off anyway. Like I said, you gotta verify all this yourself. Okay. Alright, didn't get the fronts. Let's see what's going on. Map, data. We go fronts. Alright, so maybe there were no fronts to be downloaded. They're not coming up. Alright, so this one isn't coming up right now. Let's go, let me erase that real quick. Didn't download. Okay, so there were no data from the NCEP for the frontal systems. Alright, let's go, pretty much done with this anyway. Let's go throw this. We got surface pressure back on there. But we're done with this map. Let's go over to our radar and we can pull up our weather stations on the radar live and then go from there. So alright, now this is that system over Texas. There's the Panhandle, KLBB. Alright, I want to zoom in on this a little bit. Look at these stations. We got flood warnings, flash flood warnings. So it's a flash flood statement, flash flood statement. So flash flood warning, northern Mitchell County in western Texas, southern Scurry County in western Texas until 9:45 p.m. Central Daylight Time. Alright, heavy rain. It does the whole explanation for you. This software is pretty cool. It downloads those significant weather messages, so you can put the warnings right on the screen. We can take them off if we want to save that screenshot. Now, what we want to do, there's no severe weather here, otherwise we'd have a yellow line around this. Let's go to the windows, the warning windows, and we could look at that. We got flash flood and we got special marine warnings, which are on the coastal waters. So that's pretty much it. There's no severe weather in the United States right now. So we'll stick with the flash flood warning. We'll look at this cell. Now I do have these station plots over this, so I can hold my mouse over this station. See what that is. Broken 4,700 feet, 5 miles visibility. Categories marginal BFR. I can't move my mouse to show you each thing I'm looking at because it goes away. So let me go. Should be able to maybe. I can't pull a draw tool either. Let's do this. I think once I hit my draw tool, I'm pretty much off of that. So yeah, I can't do that either. Okay. But it tells you the station, what that current METAR is at the top. It's an automated system. What time it was. Temperatures, dew point, relative humidity 88%, mostly cloudy, broken 4,700 feet, visibility 5 miles, winds are calm, altimeter is 30.13 or 1,020.3 millibars. So it shows you both of them there. So you can look at your standard atmospheric pressure, tell if you have a low pressure or not. Station pressure is 936 millibars, so we know we're in low pressure. Your theta E, temperature in Kelvin, that's used for energy measurements to determine severe weather. Also, your wet bulb temperature and your dew point depression. So your dew point depression is 4 degrees Fahrenheit. You'll only see like basically you're looking for, you'll see the dew point depression of what the difference between the temperature and the dew point. That could be any number, but once you hit 5 or less, that's when you have saturation. You can say significant cloud cover at that station. So mostly cloudy. We're mostly cloudy, 4,700 feet. Where dew point depression is only 4 degrees. So the atmosphere at that station is saturated. All right. Overcast. This one's overcast at 10,000 feet. Broken 7,000 feet. Unrestricted visibility. And I was looking. We don't have a station inside the storm right now, so we can't pull that up. But we got just the surrounding stations. Right here was one we reported a thunderstorm. No rain, just a thunderstorm. Wind 04010, gusting to 14. Unrestricted visible to thunderstorm, scattered 1700. Scattered 2,700 feet and broken 3,300 feet. This is an automated station too, but it reported a thunderstorm because it seen a flash of lightning and heard thunder. So it's got lightning distant west through north, and then shows your temperature, of course. Okay. This is for weather observations. I'm going to get into the radar. I'm going to go ahead and end the video here. I'll do a different program or another video on this radar system, so we can break that down 3D, look at the storms. That's going to be a little bit longer. I'm going to stick with this course we're doing now, so we can continue through, and now we're finished with observations. We can get into a little bit more into atmospheric dynamics. We're just going step by step with this thing, so stay tuned for the next video. I want to say thanks for watching, and subscribe to the channel and hit the bell.